So what problem do they solve? They solve an optimization problem. They say, let us find a way to choose our contracts in such a way as to minimize the overall cost. Okay? So what is the overall cost? Well, they will look at the cost of generating the production, which is given by the general cost here. And then that general cost, they allow for the possibility of even using some remedy coming from the spinning contracts to meet the load. But not necessarily. The idea is that they don't use that. Then they will allow for a higher percent of load, which is the reliability load. And now this time they will use some more spinning contracts to satisfy that, and they will solve this problem. In addition to that, there are constraints that are quite numerous, and it's a large problem. They must satisfy grid feasibility, namely the flow in each network, in each node must satisfy demands at all times. So it's a very, very large problem involving thousands and thousands of variables and constraints. One difficulty with this problem is that it doesn't allow the variables to be anything. It doesn't allow to have a contract being, I will take half of a contract and then the other half I will ignore. I will take a third of the contract. The variables have to be 0 or 1. They either take the contract or they don't. So this is a very large problem which was already difficult enough to solve, but it actually requires them to solve them with only integer variables, which are 0, 1. For people who work in optimization, this is called the mixed integer linear program. And there are some good codes, and they are presently using them to solve this problem. Actually, the reason they solve it this way, we will see in a moment, is because they solve it this way, and the whole problem procedure works in the way I've explained, is because that's the only way they know how to solve deterministic 0-1 problems. But what actually happens in reality? It happens that the load, you have to consider that the load is not certain. If you remember, the load forecaster of the ISO had actually predicted 100% for sure what the load would be. And so the whole operation, the whole decision process to which they go through is actually based on that load. And then a second possibility is that load plus the reliability. But it is actually what we observe in practice is that the demand doesn't follow their forecast. The demand actually varies quite a bit and so on. So if this is going to be not quite what they expect, they have to adjust the spinning. The reserve that they will use will require dependence on what the load would be. Similarly, to satisfy the grid feasibility, there will be uncertainty coming up. And what are the potential loads? Well, it's everything. You're going to be either anything at any time of the day above or below, not quite totally every possibility, but the number of possibilities that one can have, or precisely the load trajectory, which says how much load will be needed at a particular node up to a particular time up to 24 hours. So that is a description of the load for trajectory of the load for one day. How many of them are there? There are trillions or more. Okay? So now we're going to reformulate the problem, and it's very straightforward. We're going to find a solution which is such that we calculate for each possibility what is going to happen, and then we're going to make our contracts, which are definite, on the basis of choosing so as to minimize, in the average, the cost of having to use the reserves. Okay? So we will actually use only this minimization. That becomes not a small problem, or even a large problem. This becomes a humongous problem. And there's no way in the world you can ever find machines large enough that even will consider solving problems of this size. Okay? You have millions and millions of possibilities. Not only that, they usually want to consider not just expectation average here, they will concern the expectation plus the average value at risk, some notion of risk measure which will tell them, well, we could get in these difficulties, and if we get into these difficulties, there should be a special cost we should associate with that. So we have a humongous integer nonlinear stochastic program, and that's a challenge which is really very serious. There are no software which exists which will solve problems of this size. In addition to that, in order to do this, we must actually get a description of the uncertain load, and that doesn't exist. But everybody knows that actually that is what's happened, is that the load should be evolving with that. So the first challenge would be to describe the uncertainty. And it turns out that to describe the uncertainty, you will actually have to do quite a bit of work, and we're going to look at that for a moment. The Department of Energy, or the research unit of the Department of Energy, realized that an ISO didn't have the facilities or the people who were able to even consider problems of this nature. So they assembled a team of people in order to work on this. And our particular team, there are people who come from one of the national labs. There are some people, the ones in boldface are the PIs of this operation. The people at Iowa State University who have been doing a lot of work on predicting and working on stochastic optimization problems. People who have work at the same university I do, and some of our visitors who came from all over the world a little bit. Ignacio Rios came from Chile, Spurkel and Fabian Rüdel came from Germany. Dang visited us, Professor Dang visited us for a couple of months, hoping to help us improve our integer programming problem. This is a visitor from the École Polytechnique in France. And in addition to that, as part of the team, they put Alstom. Alstom is a software provider, and they provide about 90% of the software for ISOs all over the world. And they want that the Department of Energy insisted that we would work with them so that what we produce, they would actually go to the implementation and would make it available to the ISOs all over. And finally, as a test case, we have the New England ISO who helps us in certain instances. And then we have a couple of very clever people who actually help us in this. The rewards are enormous. If we do a good job and we are able to incorporate wind, the FERC regulations, the federal regulations are such that the ISO must make full use of wind power. And if they do, they will get about 30% of the power they need, the load they need, will come from wind. Okay? So that reduces by a tremendous amount immediately the requirement for German. Solar energy, as the prices are declining, they expect to get about 20% of the requirements for energy from solar. That the implication for the environment are immediate, and there is somebody suggested that would reduce pollution by as much as 40%, because reducing the use of coal and certain other thermal fatty. In addition to that, there are some advantages to not politically have to rely on some producers that produce coal, oil, or gas. And then finally, since the ISO is an independent system operator whose only mission is to actually provide the electricity at the cheapest possible price, the question comes up, if you actually generate this, if you change the method in which they do the dispatching, will there be a gain? And for just the New England ISO, each % of gain results in $1 billion. So if you have 3% gain, it's $3 billion. There are about 20 ISOs in the United States, and there are about 150 around the world. So this gives you an idea how much can be saved in this. The early estimates of our results have been that we can reach a gain of 5%, and I'm going to explain to you how we do this and how we arrive at this. So I'm going to spend a lot of time on the description of the uncertainty, what I denote by Xi process, which is the uncertainty